Determinant of the adjoint matrix. Welcome, everyone. Before we dive into today's new topic, let's take a moment to recap what we have already covered. In our previous lessons, we established the fundamental relationship between a square matrix, which we call A, and its adjoint, written as a J. Specifically, we learned a very important property, that when you multiply a matrix by its adjoint, the result is a scalar multiple of the identity matrix. Now, building on that foundation, today we are going to focus on a very useful shortcut. In this subsection, we are going to derive and explore a specific formula that allows us to find the determinant of the adjoint matrix directly. The best part is, this formula will allow us to find that value without the tedious work of having to calculate the entire adjoint matrix itself. Let's get started. The fundamental property. Now, before we jump into the derivation, we need to establish our foundation. To truly understand how to find the determinant of an adjoint, we must start with the core theorem that links a matrix to its adjoint. Take a look at this fundamental equation. A multiplied by the adjoint of A equals the determinant of A times the identity matrix. Let's break down exactly what these components represent so there is no confusion. First, we have A, which is our square matrix of order n. Next, we have edge A, which represents the adjoint of that same matrix A. The term on the right side, written as the vertical bars around A, represents the determinant of matrix A. Finally, we multiply that determinant by I, which is the identity matrix of the same order, n. This specific relationship is the golden key we are going to use in the next few slides to derive our final formula. Derivation of the formula. Now that we have established the fundamental property where a matrix multiplied by its adjoint equals the determinant of that matrix times the identity matrix, let's see how we can actually find a direct formula for the determinant of the adjoint. We don't want to have to calculate the entire adjoint matrix every time. That's far too much work. Instead, we can derive a much simpler formula by applying the properties of determinants to the equation we just looked at. Let's break this derivation down into logical, easy-to-follow steps. In step 1, our starting point is to apply the determinant operation to both sides of our equation. So, if we take the determinant of both sides of the equation, where a multiplied by the adjoint of A equals the determinant of A times the identity matrix, we arrive at a new expression. This new expression states that the determinant of the product of A and its adjoint is equal to the determinant of the scalar value, which is the determinant of A, multiplied by the identity matrix. We will use this new equality in the next few steps to isolate our target value. Derivation of the formula, continued. Now that we have taken the determinant of both sides in the previous step, let's move on to step 2 of our derivation. To simplify the left side of our equation, we need to use a very important property of determinants. The determinant of a product of two square matrices is equal to the product of their individual determinants. In other words, the determinant of x times y is equal to the determinant of x, multiplied by the determinant of y. Applying this rule to our equation, the determinant of A times the adjoint of A becomes the determinant of A. Multiplied by the determinant of the adjoint of A, this leaves us with the right side of our equation, which is the determinant of A times the identity matrix. Now, let's look at step 3, where we tackle the right side of the equation. Here, we need to use the property of scalar multiplication within a determinant. Notice that the determinant of A is just a single constant number, or a scalar. There is a specific rule for when you multiply a matrix by a scalar. If you have a scalar k multiplied by a matrix M of order n, the determinant of that resulting matrix is equal to k raised to the power of n, multiplied by the determinant of the original matrix M. In our specific case, our scalar k is the determinant of A, and our matrix M is the identity matrix. Therefore, when we take the determinant of A times the identity matrix, it transforms into the determinant of A raised to the power of n, multiplied by the determinant of the identity matrix. We are almost there. In the next slide, we will simplify this further by using the property of the identity matrix to reach our final formula. Derivation of the formula continued. Now that we have expanded the right side of our equation in the previous step, let's move on to step 4, where we simplify the expression using the properties of the identity matrix. Recall that the determinant of the identity matrix, denoted as the determinant of I, is always equal to 1. Because of this, when we look at our equation, the term involving the determinant of the identity matrix simply becomes the determinant of A, raised to the power of n, multiplied by 1. This simplifies our equation beautifully, leaving us with the determinant of A, multiplied by the determinant of the adjoint of A, equal to the determinant of A, raised to the power of n. This brings us to our final step, step 5, where our goal is to isolate the determinant of the adjoint of A. To do this, we assume that matrix A is non-singular, which is just a mathematical way of saying that the determinant of A is not equal to 0. Since we aren't dividing by 0, we can safely divide both sides of the equation by the determinant of A. When we divide the determinant of a raised to the power of n by the determinant of A, we follow the standard laws of exponents. This leaves us with the determinant of the adjoint of a being equal to the determinant of A, raised to the power of n minus 1. So, to summarize the derivation we've just completed, the determinant of the adjoint of a square matrix of order n is simply the determinant of the original matrix, raised to the power of n minus 1. This is the powerful formula we will be using for the examples and applications coming up next. Illustrative example. Suppose we are presented with a square matrix. Let's call it matrix A, which is of order 3 by 3. We are also given a specific piece of information. The determinant of matrix A, which we denote as absolute A, is equal to 5. Our objective here is to find the determinant of its adjoint, which we write as the determinant of edge A. Let's walk through the calculation step by step. First, we need to identify the order of the matrix. Since we are working with a 3 by 3 matrix, our value for n is 3. Second, we note the given determinant of matrix A, which we already established is 5. Third, we recall the formula we just derived in the previous slides. We will apply the formula where the determinant of edge A equals the determinant of A, raised to the power of n minus 1. Fourth, we substitute our known values into this formula. This gives us the determinant of edge A equals 5 raised to the power of 3 minus 1. Fifth, we simplify the exponent. 3 minus 1 leaves us with 2, so the expression becomes 5 squared. Finally, we reach our result. 5 squared is 25, so the determinant of the adjoint matrix is 25. Now that we have successfully derived the formula, let's put it into practice with an illustrative example to see how it works in a real-world calculation. As you can see, once you have the determinant and the order of the matrix, the calculation becomes very straightforward without needing to find the actual adjoint matrix itself. Conceptual application. First, it is important to recognize that while the adjoint matrix can feel like an abstract algebraic construct, it has very real-world applications. In fields like physics and engineering, the adjoint matrix is a vital tool used to solve complex systems of linear equations, specifically through methods like Cramer's rule or the inverse method. Next, let's try to understand the intuition behind the math. The determinant of the adjoint, which we write as the determinant of an adjoint, essentially tells us how the cofactor space scales relative to the original transformation represented by matrix A. To put this in simpler terms, think about what a determinant actually does. If the original matrix A scales a volume by a factor of the determinant of A, then the adjoint matrix scales that same space by a factor of the determinant of A, raised to the power of n minus 1. It's a beautiful way to see how the scaling property of the matrix is preserved and transformed through the adjoint process. Now that we have mastered the formula and seen it in action with our numerical example, let's take a moment to step back and look at the bigger picture. You might be wondering, why does this matter beyond just passing an exam? Key takeaways. First and foremost, remember the main formula we've worked toward. The determinant of the adjoint of a square matrix of order n is equal to the determinant of matrix A raised to the power of n minus 1. It is important to remember that we didn't just pull this formula out of thin air. As we saw in our derivation earlier, this entire relationship is derived directly from the fundamental property, where matrix A multiplied by its adjoint equals the determinant of A times the identity matrix. One of the most useful things about this formula is its simplicity. You'll notice that the final result depends solely on two pieces of information: the determinant of the original matrix and the dimension, or the order, of that matrix. You don't need to know the individual elements of the adjoint matrix itself. Lastly, let's consider the special case of a singular matrix. If the determinant of matrix A is equal to 0, and our matrix order n is greater than 1, then the determinant of the adjoint will also be 0. All right, let's wrap everything up by reviewing the key takeaways from today's lesson. Now, before you move on, please take a moment to look at the next slide, where I will highlight some common pitfalls and mistakes to avoid when applying this formula in your exams. Common mistakes. First, a very common mistake is confusing the order of the matrix, which we call n, with the actual value of the determinant. When you are calculating the final result, please be careful not to raise the determinant to the power of n. Always remember to subtract 1 from the order of the matrix first, so you are using n minus 1 as your exponent. Second, always ensure you are working with a square matrix. The concept of an adjoint and its determinant simply does not apply to non-square matrices. If the matrix isn't square, the formula we derived today cannot be used. Third, watch out for calculation errors when dealing with higher-order matrices. For example, if you are working with a 4x4 matrix, where n equals 4, your exponent should be 3, not 4. It sounds simple, but in the heat of an exam, it is easy to forget that subtraction. Finally, let's talk about the singular case, where the determinant of A equals 0. You might notice that during our derivation on slides 3 through 5, we divided both sides by the determinant of A mathematically. You cannot divide by 0. However, I want to reassure you that the final formula, determinant of the adjoint equals the determinant of a raised to the power of n minus 1, still holds true. If the determinant of A is 0, then the determinant of the adjoint will also be 0, provided the matrix order is greater than 1. Just keep in mind that the division step we use to find the formula assumes the matrix is non-singular. Now, before we wrap up today's lesson, I want to touch upon some common pitfalls. Even when you understand the formula, it is very easy to make small errors that can lead to the wrong answer. Keep these points in mind, and you'll be well on your way to mastering this topic.